Hi, in this video, we want to take a look at building autoregressive integrated moving average models. All right, so what we want to talk about in the video is that we want to go through the process step by step. I get my data and I start looking at my data, and I want to go through the entire process from beginning to end of building the model. Now, I'm not going to talk about how to handle like what your stakeholders want to see in the model. If there's any restrictions or constraints on that, that's going to be something that you'll have to navigate in a real life situation, in real time. Here, I'm going to make the assumption that you're free to make whatever model you want. All right, we're going to be working through some examples from time series analysis and its applications. Here are the names of the authors. Here's the GitHub page for the textbook and the package, and University of Central Florida students can download the textbook for free. All right, so let's get into it. All right, so the fundamental steps to building an ARIMA model is first plotting the data, specifically ACF and PACF, also just plotting the time series itself, possibly transforming the data if I need to. So specifically, we'll talk about the Box-Cox transformation, which will include the log transform. And another good one to include would be the square root transform. Then identify the dependence orders of the models. All right, so here, remember that we have three parameters for an ARIMA model. First one that we're going to need to figure out is the difference parameter, the degree of differencing. Then we figure out the ARIMA, the P and Q degrees off of that. Then after we've established the model structure that we want, we actually estimate the parameters. We run diagnostics to make sure that we have a good model. And then we compare the multiple models that we've built to each other to make a decision. All right, so the very first one I'm going to do is, of course, plot my data. We think with our eyes, so plot it. Do some plots. So plot your time series data, plot your ACF, plot your PACF. All right, so now when I go through and I plot, also I want to inspect for anomalies, missing values, anything like that. And notice that I'm going to be looking for the stationary assumption. Every time I plot, I want, whether it's the data or the difference data or the difference twice data and so on, first thing I want to check to see is if the stationary assumption holds. Constant mean, constant variance with respect to time. All right, so the variability, if the variability in the data grows with time, then I'm going to want to apply a transformation to stabilize the variance before I do anything else. And so the Box-Cox transformation frequently is a good choice for time series data. All right, and so really, you can think of the Box-Cox transformation as our goal is to make our data look more normal. All right, look like it's a more normally distributed time series. All right, so here what we're going to do, we're going to take our actual observed data and we're going to take it to the power of some numeric value, subtract by 1, and then divide by that exponent value. Now that's if lambda does not equal 0. If you apply a little bit of calc 1 to this fraction here and you let lambda go to 0 in the limit, you're going to end up getting a logarithm. And so we'll go ahead and just say that if lambda is equal to 0, the Box-Cox is the log transform. All right, so let's go ahead and say that our process looks like this. Like I end up having, this is my x of t. X of t is looking a lot like the previous observation times 1 plus some decimal value. All right, and so here it's a little bit bigger than 1. But less than 2, or it could be a little bit less, between 0 and 2 is what we're talking about. Now, if this piece of t, this other time series in there is relatively stable, one thing that I might want to consider would be to go in and do a log transform, because logarithms convert multiplication into addition. So here I could do that, boom, and now when I look at this, I realized that if I was to do the Taylor series on here, that this is approximately equal to P sub t itself. And so approximately, if I was to go through and do a differencing on here, I could get exactly what I want off of that. So when I do a differencing, subtract this from both sides, and that'll give me the difference on the left. I'm left with the log on the right, which I know is approximately equal to P sub t. And so with this log transform, I've got this off by itself, and I've got this transformed into an easier format to use. And so frequently, we will call the difference log the return rate or the growth rate because of this process in particular. Now, next thing I need to do is determine the order of the components of the autoregressive integrated moving average model. First one I want to worry about is the difference. That's the degree of differencing I'm going to use. And so what I'm going to do, I'm going to plot my original data. If I feel like it satisfies the assumptions of being stationary, I'm good. And I'm going to do an ARIMA model on the data. Let's say it's not. Then I'm going to hit differencing. And then I'm going to look at the difference data and see if an ARIMA model is appropriate on the difference once data. And then I repeat the difference twice, difference 3 times, however many times it takes for me to feel like I have a good model. Now, this is if I am confident that an ARIMA model is the correct way. It might be that as I work through this, I might come to the conclusion that this is not the correct model structure. I should try something else, like a steady state model or something like that. All right, so determine the order of differencing first. Then I'm going to build an autoregressive moving average model on the difference data after that. So we'll first determine the order of the differencing. And our primary tool for this will be time series plots. And so if I feel like I need differencing done on the original data, I'll go ahead and do that. And then I'll plot the difference data and check to see, is it appropriate to do an autoregressive moving average model? If there's additional differencing necessary, then I'll go ahead and difference again, plot it, and check to see if an autoregressive moving average model is appropriate. And I'll keep on doing this as many times as I need to, until either I conclude that this is the wrong model structure, or I get something that I feel confident in modeling. Now, be careful not to over difference your data, because we can actually introduce dependence when there isn't one. So consider the situation where I just have white noise for my time series. Well, the difference value here, if I think about it, that's actually an MA1 model. And so even though the original time series was just noise, the difference value has a structure of a moving average 1, which would, could lead me to incorrectly building an MA1 model when I should have just said, hey, this is noise. We can also use the sample autocorrelation function to help us indicate whether differencing is needed, because this polynomial has a root of unity. The sample autocorrelation function will not decay to 0 as fast as h increases. Thus, a slow decaying autocorrelation function is an indication that differencing may be needed. So if I see a slow decay in my autocorrelation function, that's an indication I need to do differencing. And differencing d times will remove this portion of the polynomial altogether from the autoregressive portion of the polynomial. And so when I look at the updated plot after differencing, I should see that it will decay faster if I did the right differencing. Now, after differencing, the next step is to look at the sample autocorrelation function and partial autocorrelation function for your difference data, and then check to see, do we have those cutoffs to determine if I have the right, or to determine what type of model I should have. If we see that the autocorrelation function cuts off after a lag of Q, I want to do an MAQ model. If I see that the partial autocorrelation function cuts off after a lag of P, I want to do an autoregressive model purely. Now, if both of them kind of tail off and I have decay that's fast enough for me to believe that an ARIMA model is appropriate, if both of them tail off, then I'm going to go ARIMA. Now, realize that it cannot be the case where both ACF and PCF cut off. All right, and because we're dealing with estimates, it's not always clear whether either one of them is tailing off or cutting off. We don't, it's not really 100% sure. It's kind of a gray area, rather subjective. And believe it or not, two models that seem very, very different can actually look very similar. This is because of that causal invertible aspect of time series. So remember that causal, in invertible enables me to represent either the x terms time series as a series on the white noise, or the white noise time series as a series on the x's. And so because of that, we might actually get two very different looking models, but in fact, because of invertible causal, they might actually be practically the same. And as we go through this, don't worry about being super precise on your model selection aspect of this. Try several different models and see what ends up working out. And so come up with some preliminary values for P, D, and Q, and then estimate the models, check diagnostics, check what works, what looks like it's solid, go with your best model. All right, so let's go ahead and run analysis of the G and P data. So let's consider analyzing the US G and P from 1947 to 2002. We've got just over 200 observations. And this is gross national products in billions of chained 1996 dollars, and things have been seasonally adjusted. And so the data was originally obtained from the Federal Reserve in St. Louis. All right, so let's take a look at the time series plots. Because the strong trend tends to obscure other effects, it's difficult to see any other variability in the data except for the periodic large dips in the economy. And often it is the growth rate or the percent change rather than the actual adjusted value that we're really interested in real time when we're looking at the economy. And so this trend going upward from left to right is obscuring like other aspects of the time series, because we just see that overall trend. But if I'm zooming in real time, like I'm living in the economy as things go on, this trend doesn't really have an impact on me because there's these fluctuations up and down, and things are changing. And so now here we can see that the autocorrelation function is not tailing off. It's not decaying very quickly. But we see that the partial autocorrelation function is cutting off quite quickly at, let's see, it cuts off at, it's gone at 2. So, this is just, I've got a strong value at 1. And so here's some output for the plots. And so something to notice is that here, this is like, pretty solid, going down. It's pretty constant stair-step effect. Notice that if I was to go in and instead I do the numbers 1 to 250, visually, I get a pretty similar autocorrelation function. So it's almost as if it's a constant step down the stairs in my original data. And notice I get a similar cutoff in my partial autocorrelation function. All right, so let's go ahead and consider the growth rate. So we're going to take the difference of the time series after I take the logarithm. So I'm going to take the logarithm of my time series. Then I'm going to apply differencing. And then I'm going to check to see what's going on. So notice I take the log, then I take the difference of the log, and I drop that into my time series plot. All right, and so this looks relatively stable in mean and variance. There might be more variability on the left considering how tight this is, but let's go ahead and proceed. All right, so looking at this, we might conclude that the ACF is cutting off at lag 2 and the partial autocorrelation is tailing off. This would suggest we would go with a moving average 2 model, or we could say that log of G and P follows an ARIMA 0, 1, 2 model. So here, this is the degree of the differencing. We have no autoregressive and we have a moving average 2. Rather than focus on one model, we'll also consider an autoregressive model on the differencing. And so we could also say that the ACF is tailing off and the PACF is cutting off at lag 1. And so that would indicate an autoregressive 1 model. All right, so let's take a look at that. So here I'm doing the difference of the log. And so here we can see the autocorrelation function. It's not 100% clear which one is the right one to go with, but this looks like an MA1. This looks like, yeah. So this one looks like, because of the cutoff, an MA2. All right, so let's go ahead and fit a model. So here I'm doing the MA2. You notice I've got 2 white noise terms shifted backwards in addition to the one that we currently have. And so if I sit there and I drop this into R and fit the model, this is what we'll get. And we've got just over 200 degrees of freedom. And statistically, all of the coefficients are significant, including the constant. Now, something that is important for us to realize is that not all packages will slap in this constant value. And so I need to make sure I know what my function is doing if I use a different package or different software than the ASTSA package. And so some packages assume by default that there is no drift. Now, in this situation, when we looked at that, we definitely saw a trend. So not including a constant would lead to the wrong conclusions about the nature of the U.S. economy. Not including a constant assumes that the average quarterly growth rate is 0, whereas the U.S. GNP average quarterly growth rate is about 1%. All right, so here, let's go ahead and fit. This is post log transform, post difference data. I'm going to fit a degree 2 moving average model. Notice that I've already taken care of both steps of logarithm and transformation and differencing. And so here I can look at my standardized residuals. I want to see no correlation between them. Here's the autocorrelation function on the residuals, and here is the normal QQ plot of the standardized residuals. So here, this may be a little bit, the tails are not quite normal maybe, but this is okay for, most of the time, real data doesn't behave as well as we would like. So I'm okay with it for now. And now here, this is a test for the p-value. This is a hypothesis test considering like 1 through capital H of the lag values of the autocorrelations. So what could happen is that if I look at my autocorrelation function, I could have all these teeth be just a little bit short of crossing the dashed line. It needs to be a little bit short of crossing the dashed line, up and bottom, up top and below. And they're so all really, they're all like individually smaller than the threshold, but they're all really close to that threshold. Well, cumulatively, we would say that there's something going on, even though individually it's not enough of a signal. Well, this test works to address that. And here it's taking into consideration the 5 steps back, 6 steps back, and so on. And so here is the outputs. So we can see statistical significance of each of the terms and the constants. Now, something to notice is that there's an AIC here and there's an AIC here. When you go to actually pull out the model itself, this is the AIC for the model as a whole. And now I want to do exactly the same thing, but I'm going to go ahead and let the function take care of the differencing. And you'll notice that here I'm doing the log transform, but I don't take care of the differencing. I'm letting the function do it for me, which I feel is a better way to go. And so basically we get the same thing. All right, now if we look at the autoregressive 1 model, this is what we're going to get. So here's that autoregressive term here. Now we're going to get a constant. And here, if we just kind of tinker with the original values, we can get things to look a little bit clearer to interpret. Or at least for comparison. And here I'm taking the difference log data. So I have done a logarithm and difference the data myself. And then I'm running the autoregressive model. I'm not letting the function take care of the differencing for me. And now I get my standardized residuals, I get my autocorrelation function, and I get my standardized residuals. Now, when you look at these plots, you'll be like, hey, doesn't that look a lot like what we saw before? Yeah, it does. It does. We'll talk about that in a moment. And so here's our outputs, and we can compare our 2 models using AIC or corrected AIC or BIC. And here I'm running through the same model that I did for autoregressive 1, but I am letting R take care of the differencing for me, but I take care of the logarithm myself. And we get exactly the same output as we just looked at a moment ago. And here's the output. We see statistically significant. Everything's looking good. All right, so now I noticed that these 2 models on those diagnostic plots looked a lot alike. And I'm kind of wondering about this. So you know what, since the coefficient in the AR1 is less than 1 in magnitude, this is a causal model. Okay, well, if I was to go through and do the causal transformation that we have here, so I'm replacing x sub t in the process with the series on white noise, I realize that I get something that's actually pretty close to the model I had before. All right, so this, if I was to replace the autoregressive portion of my fitted model with the white noise series from being causal, I'll end up getting this process. Okay, well, now take a look. Here we have 0.005, 0.008. We have a 0.3. We have a 0.3, 0.2, and it's not quite 0.2, but things are close. They're not exactly the same. And realize that I am cutting off, a lot of white noise terms when I do this approximation step. And so what this is saying is that the 2 models are close to each other because of that causal aspect. And so here I can actually look through the I can look at the coefficients for the psi weights if I want to help show this bridge between these 2. And so my next step after I've come up with some models to consider, I want to do model diagnostics. All right, so the check model fit, we're going to look at the residuals, which are also called innovations. Okay, and so when I talk about residuals, I'm going to say the one step forward prediction is how I'm going to get the residual. So I'm going to take the observed value, and I'm going to take the prediction I would get from immediately making a prediction right before I observe the upcoming data points. So where we predict one step into the future. And then to standardize, I just need to do, divide by the square root of the error variance. That gives me my standardized values. If the model fits well, standardized residuals should behave like an IID sequence with mean 0 and variance 1. And so we want to look at the time series plots to make sure that there's no obvious contradictions to this IID situation. Now, unless the time series is Gaussian, it's not enough for the residuals to be uncorrelated. For example, it is possible for non-Gaussian to have uncorrelated process for which values are highly dependent with each other. So what the authors are driving at with this is that if I have Gaussian data, if I have normally distributed data, and I have uncorrelated, then I also have independence. But if I don't have Gaussian data, if I don't have bell curve, I don't have normal, then uncorrelated is not enough to say independence. So we always need to be mindful of that. So, all right, so we're going to check the normality assumption by using, first and foremost, a histogram of the residuals. We'll look at the normal probability plot, the QQ plot, and we can also use that Q test statistic that we looked at a moment ago in the diagnostic plot. And so when we check for randomness, so here this is checking for like uncorrelated. We can also do a runs test, and we can run sample autocorrelation plots on the residuals, looking to see if there's patterns or there are large values, large deviations. All right, so if I have a white noise sequence, the sample autocorrelations we approximately independent and normally distributed, approximately, with 0 mean and a variance of 1 over n. So it's a good check to look at the correlation structure of the residuals in an ACF plot, along with those error bounds that we automatically get. So the primary goal at this point is to try and detect obvious departures from the independence assumption, because if the residuals are not independent of each other, I haven't captured all the structure of the time series. All right, so now let's take a look at this hypothesis test. And what we want to do, we want to evaluate if autocorrelations are different from 0. All right, and so for us, for this step right here, when we're looking at the autocorrelations, we're going to be applying this to the residuals / innovations, because that's what I want to look at. Now, when I do this, the reason why this is important is because individually, each of the autocorrelation values might be just a little bit above that threshold cutoff, or sorry, just a little bit below, just a little bit below the cutoff, but all of them are just below. If all of them are just below, cumulatively, I have something significant going on. So this is checking like an overall global aspect. And so here's our test statistic. So here I have the autocorrelation at h, divided by n minus h, take a summation and multiply by n times n plus 2. Typically, h is set to equal to 20. And under the assumption of model adequacy, this test statistic will converge to a chi-square distribution, where the degrees of freedom are going to be h minus p minus q, where h is the length that of how far back we're going, and p and q are the degrees of the autoregressive moving average model. All right, and we will reject the null hypothesis in favor of the alternative if we're greater than the 1 minus alpha quantile of that chi-square distribution. All right, so if I get something big off of this, we reject the null. Now, if we have white noise, n times the autocorrelation squared at h is going to be approximately degree 1 chi-square distributed. And so if I add them up, remember we have an addition property on chi-squared variables. Then if I add up from 1 to capital H of the autocorrelations, multiply by n, this will be approximately a degree H chi-square distribution. Now, remember that for the chi-square tests, I have to make an adjustment on those degrees of freedom, and that's where the minus p minus q part comes in here. All right, so let's look at the diagnostics of the GMP growth rate example. So we fitted a moving average 2 model, and so we notice that the AR1 model looks similar. The time series plot of the standardized residuals shows no obvious pattern. There may be outliers with a few exceeding 3 standard deviations of magnitude. The ACF of the standardized residual shows no apparent departure from model assumptions, and the Q statistic is never significant at the lag shown. And then the normal QQ plot of the residuals show that the assumption of normality is reasonable, with the exception of a few outliers. And that's what we want to gain here. So you'll notice that, it's not exactly normally distributed, but it's pretty close. And notice that since it's balanced, so I'm okay with just proceeding as if it's normally distributed. I don't see any patterns or anything going on. The ACF, it looks like we have, maybe not uncorrelated standardized residuals, and we have larger p-values for the autocorrelation test p-values. All right, now in base R, we have some other tools that we can use. There's some problems with these, and I'm not going to really talk about them much, but I'm just presenting the code just so that we have an option in case you come across this like down the road and somebody used these functions so that like you're picking up a project after someone like left the organization. Time series diagnostics is in the stat package. The author of the textbook states that there's problems with this and there's some bugs, so we should not use it if we don't have to. There's also the box test that we can run this with. But honestly, the ASTSA package is better for running our diagnostics. Now, another thing that we can do when we run our model selection is that the forecast package has an auto.arima function that it actually will go through and it will estimate your model for you. It will estimate what is the degree of differencing, what is the degree of autoregressive, and what is the degree of moving average for us, so we can drop this in. And if we choose to do that, we're going to get a degree 1 differencing and an autoregressive 1 model if I drop in the GNP data, the log GNP. All right, so let's go ahead and take a look at the diagnostics for the glacial time series that we've looked at before. And here, we're going to fit a degree 1 differencing with degree 1 moving average model on the logarithm of the data. So I'm taking log, taking differencing, moving average 1. There appears to be a small amount of autocorrelation left in the residuals, and the Q test gives us significance. And so we notice when we get down to here that there's some autocorrelation still going on, and we can see that in this plot. Notice how things tend to stay below 0 or they tend to be above 0 in groups. Here's the output on this. And so we might want to try an ARIMA 111 model. And when I do that, I notice that now I have no statistically significant autocorrelations. Things have improved. I have less clumping, but to my eyes, it looks like there might be a little bit of clumping on each side of 0, but I feel better about it. No model ever looks perfect. Here's the output on that. And now I can compare the two models using AIC and BIC. When I look at this, remember AIC and BIC, we want the simpler model, we want the least value. And so here, this indicates the more complicated model with autoregressive is the one to go with for both AIC and BIC, which makes me feel like this is going to be the right model to go with of an ARIMA 111 model. All right, well, that's all I've got for you. Life is short, do math.